Welcome to the deep dive. Ever wonder how those incredibly strong but really lightweight materials are made? The kind you see in airplane wings or maybe even bridges.
Yeah, it's fascinating stuff.
Today we're diving into sandwich structures. Think of like a tough but light filling between two strong outer layers.
The composite sandwich, essentially.
Exactly. Specifically, we're looking at materials with GFRP skins, that's glass fiber reinforced polymer,
Okay.
and a PU polyurethane foam core in the middle.
Mm-hmm.
We've got this really interesting study from Ms. Moody and colleagues in the Fracture and Structural Integrity Journal. They properly put these materials through their paces.
They really did. They used a technique called Digital Image Correlation, DIC.
Ah, DIC. Okay, what does that let them do?
Well, imagine watching exactly how every tiny part of the material moves and strains as you stress it. DIC basically lets you do that. It gives you this incredibly rich picture, much more than just the overall force.
Right, you can see where it's failing. So our mission today is to understand how these composites handle different stresses, pulling, squashing, sideways forces,
All the key loads.
and what that means for using them in, say, real-world construction projects, civil engineering applications.
Okay, so where should we start? Maybe the skins.
Good idea. Let's look at those GFRP skins on their own. They tested them in tension, pulling them apart, and compression. What did the tension tests show?
Okay, so when pulled, the GFRP was pretty consistent. It went through like 3 stages. First, it just stretched elastically, basic stuff.
Like a rubber band. Yeah.
Exactly.
Yeah.
Then small bits of damage started happening inside, so the behavior became nonlinear. And then finally, it failed. Snapped.
Okay. Any numbers on that? How much force?
Yeah, on average, it took about 151 megapascals of stress. That's quite a lot. And it stretched about 2.7% before breaking.
And could they see how it broke?
They did, yeah. Using microscopy, they saw things like irregular fiber distribution, fibers pulling away from the matrix material, fibers actually breaking and pull out. DIC also clearly pinpointed the strain, concentrating right at the fracture spot just before it went.
Interesting. Okay, so what about when they squeezed the GFRP skins? Compression.
Again, sort of similar 3 stages, but interestingly, they were actually stronger in compression.
Really? How much stronger?
They held up to around 227 megapascals at about 3.4% compression. So yeah, quite a bit tougher under squeezing.
And the failure was different too, I imagine.
Definitely. Instead of just snapping, you saw layers splitting apart, some internal cracking, fibers breaking, yeah, but also this thing called kink band formation. It's like the fibers themselves start to buckle on a tiny scale.
Ah, microbuckling.
Precisely. And the DIC showed, as you'd expect, the highest compression where the load was applied, but also some local buckling, a bit of bulging in the middle.
So those GFRP skins, pretty tough, especially under compression. What about the filling? The PU foam core, it sounds kind of squishy.
It is, relatively speaking. They tested that by squashing it flatwise. The key thing is its behavior under load. It has an initial elastic response, then this long plateau phase where it crushes easily.
Like bubble wrap popping.
Sort of, yeah, like the foam cells collapsing. Then finally it densifies and gets really stiff. It could handle about 0.44 megapascals of stress, but it compressed a lot down to like 70-something% of its original thickness.
Wow, okay, so its stiffness, its modulus, is much lower than the skin.
Oh, much lower. Around 4.19 megapascals for the compressive modulus.
Right, so now we know the parts. How did the whole sandwich structure behave when they squashed it flatwise, pressing on the big surface?
Well, interestingly, the load curve looked a lot like the foam's curve at the start.
Ah, suggesting the core takes the initial hit.
It seems so, yeah. Core damage first. You see those same 3 phases, again. Elastic, the plateau where the core is crushing and densifying, and then a rapid load increases, everything gets packed tight.
And the overall strain.
Average ultimate strength was about 21 megapascals, again at that sort of 70% thickness reduction.
Did the skin stay stuck to the core? That seems important.
It did, yeah. ASTM images showed really good skin core bonding. Even while the foam cells inside were collapsing extensively, they saw maybe a few tiny microcracks in the skin, possibly from little voids, but no major debonding.
And DIC, what did that show?
DIC showed the displacement concentrated at the top plate pushing down, and you could actually see the foam sort of expanding outward slightly at the sides. The strain maps really highlighted that foam densification process.
Okay, one more test. Edgewise compression, pushing on the thin edge. Sounds like buckling waiting to happen.
Exactly, and geometry played a huge role here. They tested 2 shapes. One was basically square in profile, S60 they called it. The other, S200, was much longer and thinner.
And they behave differently.
Massively different. The squarish S60 samples mostly failed by localized buckling. You'd see a bulge form, maybe some skin cracking near it, sometimes a bit of skin core debonding. They failed at an average strength of about 85 megapascals.
Okay, so still quite strong. What about the long, thin ones?
The S200 samples, they buckled globally. The whole structure bent sideways, like an Euler buckle in a column.
Ah, the classic ruler buckling.
That's the one. And because of that, the ultimate load, the strength, was way lower. Only about 14.5 megapascals on average.
Huge difference, just based on the length.
A really significant impact. DIC, again, showed it perfectly localized, bulging in the middle for the S60, but this much larger, broader sideways displacement for the S200, confirming that global buckling.
So wrapping this up then, key takeaways seem to be. First, DIC is incredibly useful for seeing how these things deform and fail.
Absolutely invaluable.
Second, the GFRP skins themselves are actually stronger when you squeeze them than when you pull them.
Which is interesting for design, yeah.
When you compress the whole sandwich flatwise, the foam core takes the initial load, but the skin core bond holds up really well.
Good adhesion, critical for performance.
But if you compress it edgewise, the shape is king. It determines whether you get local buckling or that much weaker global buckling mode.
The aspect ratio is crucial there.
Right. So this all makes me wonder, and here's something maybe for you, the listener, to think about. How could you actually tailor these structures?
What do you mean?
Well, could you, say, change the GFRP layup, maybe make it thicker in some places, or vary the density of the PU foam core strategically?
Functionally graded material.
Yeah. Could you design it to optimize performance for very specific loads you expect in a real building or bridge, tailoring the strength and stiffness just where you need it most?
That's a fantastic question. It's really pushing into advanced composite design, optimizing the material structure itself for the application. A great challenge.
Definitely something to mull over. Thanks for walking us through that research today.
My pleasure. Really interesting work.